over the review questions. Remember, this is laid out with linear form trig equations first, but before we jump into the trig, we're just going to review basic solving equations in linear form, and with just x as the variable. So when you have multiple x terms, okay, you want to combine like terms. These happen to be on the same side of the equation, so we don't have to move anything. We can go ahead and combine those. And then if there's any constants, you can combine. We're going to combine those. So that ends up being negative 5x, and that ends up being a plus 1. Once everything on both sides of the equation is combined and simplified, then you start moving things across the equal sign to isolate the variable. In this case, the x. So we want to get x by itself. We'll subtract the 1 over. Then we would get rid of the negative 5 coefficient by dividing. We've isolated the x. That's just negative 2/5. We'll do the same thing on number 2. We want to simplify both sides, and then we'll start moving things. Here, there happens to be some parentheses. We can distribute that 4 into. We've got 20x minus 8. No like terms to combine over here, so I'm ready to start moving terms to isolate the x. So opposite operation is going to be to add the 8. And that'll be negative 8. And then get rid of the coefficient by dividing. And then this can be reduced. We can figure out 4 goes into both of those. 4 goes into 8 twice and to 25 times. Now on this other one, there's nothing to combine over here. I'm going to get rid of the 1 by adding it to the other side. Now that square root of 2 is under the radical, the x is not. So then I divide out that coefficient of radical 2. We don't leave radicals in denominators. And when we get to trig questions like this, if you have one where you end up with a radical in the denominator, you definitely need to rationalize it because it's not going to be a unit circle value that you recall. But if I go to multiply this by the radical 2 in the numerator and denominator, that becomes 3 root 2, and then this becomes over 2. All right, here now when you have variables on both sides, there's nothing to simplify on the left or right individually, but I need to move things across the equal sign. So I'm going to move the x's to the right because this is the smaller x coefficient, and so when I do that, I'll still have a positive coefficient. You could do it the other way, but then you'd have a negative you have to get rid of. It doesn't really matter though. You'll end up with the same answer if you moved all the x's to the left and the numbers to the right. So 9 minus 2 is 7. Now we've moved the x's to the right, so we'll move the constants to the left. And then you're ready to divide out your coefficient of 7 to get x by its lonesome, which gives us 3. All right, so now we're going to try the same process with trig equations. So the algebra does not change. It's just a trig expression instead of an x as our term that we're trying to isolate. And then once you isolate it, it becomes a unit circle question where you have to know your unit circle values. So for this first one, sine of x is what I'm trying to get by itself. So I'm going to get rid of this 2 by dividing. So I have sine of x equals root 2 over 2. So I've accomplished the goal of isolating the trig function. Now it's the unit circle question. So you look at your complete unit circle. Excuse me. You look at your complete unit circle and you ask yourself, where is sine root 2 over 2? And they tell you right here, they want it on the interval from 0 to 2 pi. So we're in radians. We're going to give radian answers. And it's 1 revolution, 1 trip around that unit circle. So you can look at your unit circle. Remember, sine corresponds to the y values of the ordered pairs. So you're looking for where the y values are root 2 over 2. That happens at 45 or pi fourth reference angles. And the fact that it's a positive root 2 over 2 tells me that it's quadrant 1 and 2, because that's where sine is positive. So that is at pi fourths from quadrant 1 and 3 pi fourths from quadrant 2. So on number 6, I've got cosecant on both sides. I can't combine them. I need to get them to the same side before I can combine them. So I'm going to move the 2 left off a C there. Cosecant x to the other side by subtracting it. So 3 minus 2, so that's just 1 cosecant x equals root 2. Now, cosecant is not one of the 3 trig functions that we have labeled on our unit circle or that we have tried to memorize, but it's the reciprocal of sine, which is 1. So I can just take the reciprocal. The reciprocal means flip the fraction. So right now this root 2 is understood to be over 1. So when I flip it, it's 1 over root 2. Now again, I don't leave radicals in the denominator. So multiply by root 2 and end up with root 2 over 2. That's a value I should recognize. Hey, that's actually the same as this problem. Sine of x equals root 2 over 2. So our solution, our answers are going to be the same because it's on the same interval here as well. So that again will be pi fourth, 3 pi fourth. All right, on number 7, we've only got sine of x in one spot, so I'm ready to move the terms away from it. So I'm going to subtract 1 from both sides. Just going to give me 4 sine of x equals negative 2. Then I'm going to get rid of the 4 coefficient. And that's going to reduce. 2 over 4 is 1/2. So I end up with sine of x equals negative 1/2. So where is the sine value negative? That's quadrants 3 and 4. And at what reference angle is it 1/2? That's at your pi sixth or your 30 degree. So it's the pi sixth reference angle from quadrants 3 and 4. That's 7 pi sixths and 11 pi sixths. All right, on 8, I'm going to isolate cosine, so I'm going to add the 5 to both sides. Now, this one doesn't make sense. There is nowhere where cosine is ever 5. If you think back to graphs of trig functions, which we did in Unit 3, you should hopefully recall that this is the cosine graph, or at least one cycle of it. And the highest that it goes is 1, and the lowest that it goes is negative 1. Cosine's range is negative 1 to 1. So 5 is not in that range. 5 is way up here off the screen actually. So cosine is never that high. So this one has no solution. All right, then we're going to move into quadratic form. So it's not just x, it's now going to be x squared. Okay, or x squared and x. Okay, in the trig, when we get to the trig ones, instead of just being a trig function, it's going to be a trig function squared. So let's refresh on your factoring processes. This first one, I can solve two different ways. I can factor because this is the difference, meaning it's subtraction of two perfect squares. Or I can just isolate the x, since there's only one term that has an x in it, which is most likely the method y'all are going to use. So the minus 121 gets added to the other side. The 25 needs to be divided over. Here's where it gets tricky, where a bunch of people make a mistake is to get rid of that square root, or excuse me, that square, you take the square root. And when you take the square root in the process of solving, you have to remember to put plus or minus in front. If you forget that, you're going to be missing out on half your solutions. So here, when we take the square root of a fraction, you need to remember that you take the square root of the numerator and the denominator. So this is going to be plus or minus, and then the square root of 121 is 11, and the square root of 25 is 5. So that's 11 over 5. By 10. Now 10 is different because it's not just an x squared. There's an x squared term and an x term and a constant. This is your trinomial form factoring, which the a value is an understood 1 right here. And when that's the case, I think it's easiest not to worry about trying to do box method or grouping or anything with your x table or anything like that. The only factors of 1 are 1 and 1. So 1x squared, the only factors are x times x. So then you're just to a point where you have to ask yourself, well, what are the factors of -5 that add to 4? So the only factors of 5 are 5 and 1. So then I just have to think about the sign. I need it to multiply to a negative, so these need to be opposite signs, but I need it to add to a positive 4. So I want the 5 to be positive and the 1 to be negative. And this is equal to 0, and once you've factored it, you split and solve. So you set each factor individually equal to 0 and solve. So here I would add 1 to the other side. So I get x equals 1 as one of my solutions, and then here I would subtract 5. So x equals -5 is another solution. All right, here's another trinomial factoring with an understood a value of 1. So you know that that's going to factor to x times x. So now we're just asking ourselves what multiplies to give us -28, or excuse me, positive 28, and adds to give us 11. So the factors of 28 could be 28 and 1, not going to give us 11. It could be 14 and 2, not going to give us 11. It could be 7 and 4. 7 and 4 would add to 11, but I need it to add to -11. So I would need both of them to be negative, because when I multiply those, it would give me positive, but when I add them, it would give me -11. So now I'm ready to split and solve. So here I would add the 4 to the other side, so I get positive 4. Here I would add 7 to the other side. All right. Here, this one is not a trinomial. There's not a constant. It's just an x squared and an x term. So I don't have to do this trinomial form factoring. I can do GCF factoring. These two terms both have something in common that they can both be divided by, and that's a 5 and an x. So the 5x, the greatest common factor, gets to come out, and then you put in parentheses what's left when you divide by that. So if I were to divide this by 5x, each of these terms, okay, here the 5's reduce, and the x squared over x reduces to just x. And I've got plus, then here the x's reduce, and the 10 over 5 is a 2. Now it's factored. I can do the same split and solve. On the right side, I would subtract the 2 to the other side. So I end up with -2 as a solution. And then over here, I would divide by 5. And so it's still 0. 0 divided by anything is still 0. So now let's try it. Oops. Well, to draw this. There we go. Try it with trig now. So number 13, there's only one trig term, sine of x, and it's sine squared of x. I need to isolate that. So this one I'm going to be able to solve by doing that square root. So I need to subtract the 9 over first. That gives me 1. Then I need to take the square root, and I need to remember plus or minus in front. So that square and square root cancel each other out. So I've got sine of x equals positive or negative. And then the square root of 1 is just 1. So now it's the unit circle question. I'm looking at the unit circle and I'm asking myself, where is sine positive 1? And where is sine negative 1? Remember, sine's the y value. So it's 1 at the top of the unit circle and it's -1 at the bottom of the unit circle. So that's at pi halves and at 3 pi halves. Okay, number 14 is very similar. There's only the cosine squared x. It's the only trig term. The rest of these numbers can be moved around to isolate it. Then I'm going to get rid of the 4 by dividing. And I'm going to take the square root, get rid of the square, and that's going to make a plus or minus over here. And again, remember, when you take the square root of a fraction, you're square rooting the top and the bottom. So the square root of 1 is 1, square root of 4 is 2. And now this is just cosine of x. So now it's just, where is cosine 1/2, positive or negative? It doesn't matter, the sign. So I'm actually going to have 4 solutions here, because it can be in all 4 quadrants, because in quadrant 1, there's a place where cosine's positive 1/2. In quadrant 2 and 3, it's negative, and then in quadrant 4, it's positive again. Okay, so we're going to have 2 solutions from the positive 1/2 and 2 solutions from the negative 1/2. Remember, cosine corresponds to the x value of the ordered pair. The x value of the ordered pair is 1/2 at pi thirds. So it's the pi thirds angle in all 4 quadrants. There you go. Okay, let's do one more where there's just an individual trig function squared. So I'm going to add the 2 to the other side. Divide out the coefficient of 6 here. And that's actually a 1. Anything divided by itself that reduces, it's a 1. I just don't have to write the 1 over here, because 1 times tangent squared is just tangent squared. And then I take the square root and I remember to put plus or minus in front of it. So I end up with tangent of x equals positive or negative 1. So tangent is 1 where sine and cosine are equal. That's at your pi 4th reference angle. But the fact that you got that plus or minus here, that does not eliminate any quadrants. That means we're gonna have a solution in every quadrant. So at every pi-4th reference angle. So 1, 3, 5, and 7 pi-4ths. All right. Next up, we've got two trig terms. One is squared and one is not. So I can't just isolate one of them. They're both actually already isolated. So when that's the case, when you can't just isolate one of them, when you have a quadratic form, you need to get them to the same side, set equal to 0. So I'm going to subtract sine x to the left side. So I'll end up with sine squared x minus sine of x equals 0. I subtracted that over here, and I can't combine these because one is squared, one is not. But now I have a GCF, greatest common factor. Sine of x is in both of those. So when I divide that out, this would be left with a single sine of x minus, and then that would be an understood 1. So then I'm ready to split and solve. On the left side, the sine of x is already isolated, but over here I need to add that 1 to the other side. So now I've got them isolated and I'm ready to answer the question, where is sine 0? Remember we said sine's the y value, so where's the y value? 0. That's on the right and left hand sides of the unit circle. So that's at 0 and pi. Okay, where's sine positive 1? Now this is only positive 1, so it's just the top of the circle, which is pi halves. All right, almost done. Here now we've got a trinomial form. We've got a tangent squared, a tangent, and a constant. So it's going to work the same as if those were x squared and x instead of tangent squared x and tangent of x. So treat it the same way. Our a is still an understood 1 there. So this tangent squared can only possibly factor to tangent x times tangent x. And the only possible factors of 1 is 1 times 1. Now, I need them to be the same sign to multiply to a positive, and I need them to add to positive 2, so I want both of them to be positive. So here I actually end up with two identical factors. I don't need to solve both. They're exactly the same. I'm just going to solve it once by subtracting that 1, and then answering where is tangent -1. So again, tangent is 1 at the pi-4ths reference angle. Tangent is negative in quadrant 2 and 4. So the pi-4ths reference angle in quadrant 2 is 3 pi-4ths. And the pi-4ths reference angle in quadrant 4 is 7 pi-4ths. All right, last but not least, here is one where we have multiple trig terms, but it's not a trinomial. I have a GCF here. Both of these terms have sine of x as a factor. So I can take it out, which would leave me in the first term, if I divided out sine of x, I'd be left with just the 2. And here, if I divided out the sine of x, I'd be left with cosine of x. So I can split and solve. So over here, the sine x is isolated, cosine's not. So I'd have to subtract the 2 to the other side. And this takes us back to what we said earlier. -2 is not in the range of -1 to 1. So there's no solution for this factor over here. But here, is there a place where sine is 0? There definitely is. Sine is 0, at 0, and at pi. All right, so that's solving trig equations. So then we're going to jump to inverse trig. So remember, arc at the beginning of your trig function is the same as inverse. So arcsine or inverse sine mean the same thing. Arctan, inverse tan. Arc cosine, inverse cosine means the same thing. Your refresher that you need to remember are the restrictions of inverse sine, cosine, and tangent. So remember, for inverse sine of x or theta, whatever variable is being used, is negative pi halves to pi halves. Okay, remember, sine is positive in this quadrant and negative in this quadrant. So that's where we're going to give our solutions, depending if it's a positive or a negative. Got to be between those two values. So let's go ahead and look at the inverse sine questions. So arc sine of 1. So in this range, where is the sine value positive 1? And that would be up here. And we can include pi halves and negative pi halves. Those have a bracket in the range. So my answer is pi halves. So again, it's just looking at your unit circle. It's knowing that arc or inverse means at what angle is this trig function this exact value. And your answer is an angle. So the other inverse sine is 23. So this is going to be read as, at what angle is sine root 2 over 2? Well, look at your unit circle. Root 2 over 2 is the y, or the sine value, at pi fourths. Okay, now the other thing you want to remember for inverse cosine is that it went from 0 to pi, and cosine's positive here and negative here. Okay, so inverse cosine, number 21 here. At what angle is cosine root 3 over 2? So looking at your unit circle in just these two quadrants, where's cosine positive, quadrant 1, root 3 over 2, and that's at your pi 6th reference angle. Arc tangent, or excuse me, arc cosine here, we're going to do the same thing. At what angle is cosine 1/2? So where's the x value, positive 1/2? Only between 0 to pi. So that's only going to be in quadrant 1. Cosine is 1/2 at pi thirds. Okay, and then your other restriction is for inverse tangent, and it's the same as inverse sine, except the pi halves is not a bracket, it's a parenthesis. So you can't include the ones that are on that vertical axis, just between them in quadrant 1 and 4. So arctangent, so where is tangent negative root 3? Well, the fact that that's a negative right there tells me that it's quadrant 4. So looking at your unit circle in quadrant 4, where is the tangent value, negative root 3? And that should be at your pi third reference angle, which on your unit circle, when you look at that pi third reference angle, it's going to say 5 pi thirds. But remember, we have to go in the negative direction when we're doing this inverse tangent or inverse sine, okay? Because the angles from quadrant 4 are negative acute angles. So instead of calling it positive 5 pi thirds, going in the negative direction to get there, it would just be negative 1 pi third. And then arctangent or inverse tangent of negative 1. So where is tangent? Again, negative. So that's again quadrant 4. Tangent is -1 at pi-4ths reference angle here. So that's -pi-4ths. All right. Then we're going to get into composition of inverse trig. So just remember, work inside out. Work the inside function first. Okay, so tangent at pi-4ths. So you're looking at your unit circle and saying, okay, what is tangent? And this is not arctangent or inverse tangent. This is just straight up. What is tangent at pi-4ths? And it's 1. So that's a 1. So then we have arctan, and we replace that with a 1. So now the question is, because I replaced this with this. So now the question is, remember arc or inverse is at what angle is tangent's value 1? And if we stay in that range of -pi-halves to pi-halves, it's at pi-4ths. So sometimes when you do these compositions, if it's something like arctan and tan, or arcsine and sine, or arccosine and cosine, sometimes these get to just cancel each other out. They're opposite operations, and you're left with that input is your output. That's not always the case. You have to be careful because that number has to be in the correct restricted area, or in this case, it had to be in the range for arctan, which it was, because it was in quadrant 1, so it was fine. But I'm just want you to understand that's not always just going to automatically cancel out. So here's one where it looks like, hey, this should just cancel out. We've got sine and inverse sine. Now this one is flipped around. It's the inverse is the inner function, and then the original function is the outer function. Okay, so notice that it's an exact value, not an angle measure, because the order of those is switched. We're still going to work inside out to check and make sure, can those just cancel out? So inverse sine of √3/2 means at what angle is sine √3/2? Well, sine is √3/2 at pi-thirds. And then we've still got the sine. So sine at pi-thirds, if you look at your unit circle, sine at pi-thirds is √3/2. So this is another one that did work out to where sine and inverse sine just reduce, and you're left with your output is the same as the input. Now the rest of these, they don't match. This one's inverse cosine and tangent, so there's no way these are going to cancel out. Those will never cancel out if they're not even the inverse trig of the trig function that's listed. That won't happen. So we just work inside out. So I'm going to work the inside here first. At what angle is cosine √3/2? So where's the x value √3/2? And that happens at pi-6. And so now I've got tangent of pi-6. Well, I look at my unit circle. At pi-6, what is tangent? And it's √3/3. Okay, here, work inside out. I'm going to do arc sine of 1. So where is the sine value +1? And that's at pi-halves. And then I've got cosine of pi-halves. So at the pi-halves angle, the x value, the cosine value, is 0. All right, here, inside out, what is sine of pi-thirds? So if I look at pi-thirds, the sine value is the √3/2. This should actually not be on the review because there's nowhere where tangent is √3/2 that you have memorized from the unit circle. This exists, this is in the range of tangent, it didn't have the restricted range, but it's one that you would have to type in the calculator. So you would literally type in second tangent to get inverse tangent of √3/2. You'd make sure you were in radian mode and you would get your solution. Okay, but it's going to come out as a decimal value. It is not a radian value with pi in it. Okay, so you are not going to have one that you have to type in the calculator on the test, so I'm not going to bother going through that on the review. All right, here, inside out, what is tangent at pi sixths? So tangent at pi sixths is √3/3. And then I'm doing arc cosine of that. Where is that the cosine value? And actually the same thing that happens here happens. There's nowhere that that's the cosine value on the unit circle that we memorized, that we filled in. Okay, this would be one that you have to do in the calculator, and I'm not going to bother doing it because you're not going to have to do that on the test, so we won't worry about those. All right, last but not least, just a little spiral review. Some past topics. 31 through 33 are just getting exact values of these trig expressions. This is just straight from your unit circle. What is cosine at 300 degrees? So hopefully if you look at your unit circle, that's your 60-degree reference angle, and you know that cosine is 1/2 at 60-degree reference angles. Or you can just look at it on your circle, and it's in quadrant 4 where cosine's positive. So this is positive 1/2. A sine at 7 pi sixths. So 7 pi sixths is in quadrant 3, the pi sixth reference angle. And so there I know that sine is 1/2. But it's in quadrant 3, and I know sine is negative. Or you can just look at your unit circle and see this is the answer. Now this one's a little trickier because it's cotangent, which is not written on our unit circle, but its reciprocal is. Okay. So if I want to know what is cotangent at 3 pi fourths, let me go ahead and answer what is tangent at 3 pi fourths. So 3 pi fourths is in quadrant 2, where tangent is negative, and that's a pi fourths reference angle where tangent is 1. So it's -1. Well, the reciprocal of -1 is -1, because 1/1 flipped is still 1/1. So when tangent is -1, cotangent is also -1. All right, and then the other thing that you need to be able to do is finding coterminal angles. It says find a positive and a negative coterminal angle. So remember, coterminal angles, so we say 75 degrees, that's right here. Coterminal angles is literally just adding 360 or subtracting 360 if you're in degrees. So going in the positive direction and spiraling back around to get there. So it's your original 75 plus 360. Or in the negative direction, it's almost a full circle, but it's 75 degrees shy of a full circle. That's why it's 360 minus your 75. So here I have, if I do 75 minus 360, I get -285. I want 285 degrees in the negative direction to get here. Okay. Or if I do the original angle plus 360, okay, the one that spiraled back around, I got positive 435 degrees. So there's one negative and one positive coterminal. Now this one's in radians, so instead of adding or subtracting 360, I'm going to add or subtract 2 pi. If you need the visual, let me sketch it for you. 3 pi fourths is right here. Okay, so if I want to add a full circle to that to get my positive coterminal, you can think in terms of fourths if that's easier. So a full circle, which is 2 pi, would be 8 pi fourths. So I add 8 pi fourths. Okay, which is adding a full circle. So 3 plus 8, because I've got a common denominator of 4, is 11 pi fourths. So that's the positive coterminal. Now to get this angle in the negative direction, you can think, oh, this is 1 pi fourth past a half circle, which is pi, or 4 fourths. Okay, or mathematically, you can say, well, adding a full circle or subtracting a full circle. So 3 minus 8 is negative 5 pi 4. So you have one positive and one negative coterminaling. All right, so that is it for the review.